Yeah, thank you, Sebastian, and thank you guys from the Active for Water for the invitation. Good morning, everyone. I'm Jurij, as I was introduced, and I want to talk about our spin-out journey or spin-out in the making, CAVI. So, up the outline of today's talk, I'm going to tell you about a quick introduction. Then we're going to look at what cavitation is and how it can be applied. Then we're going to switch to our solution. And after that, we're going to do a deep dive on our journey. And I'll also talk about just a little bit about the spin-out ecosystem at the University of Ljubljana. And at the end, we'll try to see if we've learned some lessons within this path. So uh, I don't know, a quick thought. So hidden within the physics of these collapsing bubbles, collapsing cavitation bubbles, is a powerful tool with the potential to disrupt conventional industrial processes. And while cavitation might seem destructive, it could become a key to transformation in water, energy, food, pharma, and even medical technologies when we learn to manipulate it. So first of all, as we talked about before, what is a spin-out? A spin-out is a company formed based on academic research generated within and owned by the university. And why would someone want to do or to make a spin-out? Well, I would say that one part of the drive of every researcher is to put his scientific work to life. And to do that, in one or another way, at least in our technical sciences, that means that there needs to be a presence of a company. Usually it could be, I don't know, an outside company, corporation, or one of your industrial partners that is interested to implement the technology or the innovation in his process or his project or at the end into his product. But in my opinion, creating a spin-out is one of the purest executions of this drive. So you need to identify a team or an individual with high enough commercialization drive to invest his time and his effort to form a spin-out, and then you need to fight and bite and work really hard. But yeah, enough romanticizing. Let's get to the hard facts. So CAVI, our spin-out company in the making, in the progress, is for now an attempt of a spin-out startup at the Faculty of Mechanical Engineering, University of Ljubljana. And our main purpose is to leverage the immense amount of cavitation knowledge and know-how and to build a product around it. So we seek currently we seek potential applications in different industries and with a problematic liquid where cavitation could be applied in an economically feasible manner. Our bet is that cavitation can be implemented in a process to provide like a net gain. And that means that, of course, we first need to identify this process, then diagnose critical points, and then tailor our cavitation reactor or our solution to efficiently solve this issue. With that, we are looking for, I don't know, 10x solutions. That means that we do 10 times improvement, so 10 times faster, 10 times less energy, 10 times better. So who is working on that? We are coming from the Laboratory for Water and Turbine Machinery from the University of Ljubljana, Faculty of Mechanical Engineering. And our core team consists of Tadej, our ex PhD student who is working currently. He moved to Greece for love reasons, and he's an expert in European research and innovation funds, so he's working on funding. Recently, we onboarded Stash, who has previous experience with his own startup, Lumo, and myself. But that's not all. We have like a very dedicated team behind us. So we have an immense support from our laboratory, so laboratory for water and turbine machinery. With us is also Mojca Zupans, who is our science advisor. Professor Mateusz Dular, who is our senior science advisor. And last but not least, we would like to acknowledge our ex-boss, Brane Širok, who is like all fronts advisor, not just science. And he's also the one who, I would say, started this drive of the research and the solutions that originated from the university to push them towards industrialization. Okay, let's first briefly look at this first part. So what is cavitation, how it could be applied, and what is our solution built on that. So cavitation is in one way similar to boiling. So we are looking at evaporation or this phase change phenomenon, as you can see on the right. So if you look at boiling, boiling can be achieved in two ways. So you can increase the temperature to come to the boiling point, or you can reduce the pressure. But in contrast to this very soft dynamics or soft behavior of the boiling vapor bubbles, cavitation is known for the so-called cavitation bubbles, which are very typical for their rapid dynamics. So here in the video, you can see one such example. And just to illustrate, so we've got small, less than a millimeter big bubbles that are induced by the rapid pressure change. And these bubbles tend to collapse. They're prone to collapse. And this collapse happens in a very short amount of time. For example, less than a microsecond. When the bubble collapses, an enormous amount of energy is transformed. And that means that enormous temperatures and enormous pressures are present in this so very small and very short amount of this cavitation bubble collapse time. So, and when this energy transformation occurs, the interesting things happen. So cavitation has its mechanical, thermal, and chemical effects. So mechanical, it could be the mechanical could comprise of pressure wave, pressure shocks. The thermal is due to the increased temperature, and because of these two, also chemical effects can be present. When we're talking about chemical effects, we mostly think of the presence of hydroxyl radicals, which occur as a result of the cleavage of a homolytic cleavage of a water molecules, and these radicals carry on or hold a big oxidation potential. In typical engineering terms, cavitation is considered a bad or a negative phenomenon because it usually induce some kind of cavitation erosion or cavitation damage. As you can see in this example, it's typical for the turbo machinery, and on the top right you can see a damage of a ship propeller which was induced by cavitation. And it's not just damage. It's in the case of, I don't know, hydro pumps or hydro turbines. It's the cause of noise, efficiency, reduced efficiency, reduced performance, increased energy consumption, reduced output performance, stuff like that. Yeah, and another, I would say, like the biggest or the most impactful cavitation damage occurred in a spillway. So this is the case of Glen Dam spillway channel, which was damaged in 1941. So yeah, our bet or our assumption is if the cavitation can damage these steel and concrete structures, why couldn't it be used like in a good way to do something we would like it to do? And we are not the only ones thinking of that, as the cavitation has already been exploited in nature. So I would say, well, man mostly dealt with these negative cavitation consequences. Nature has somehow learned how to exploit it. How to exploit it. So with a tiny brain of a shrimp, if a tiny brain of the shrimp could somehow master or harness this power of cavitation, why couldn't we do it? I would give a shout out to this guy Jacob Harrison here, who is performing the research on the shrimp clamping shrimp clamping mechanics and the cavitation induced the cavitation phenomenon around it, and check it out. It's amazing. So if shrimps can do it, why couldn't we? I will briefly look at some examples. So we've tried sludge treatment. Here you can see the examples of sludge disintegration in the top, and then the damage of cells or like some bacteria within this sludge on the bottom. And very typical for cavitation is particle size reduction. So here on the right top graph, you can see a typical mean diameter reduction. So for non-cavitated and cavitated samples, and specific surface area increased. So we break the particles apart. On the chemical side, the effect is usually an increased soft dissolved fraction of the chemicals, so increased soluble COD. Then we've got again, we worked a lot on bacterial destruction. Here we can see more than 3 log reduction of E. coli and Legionella. We also worked on virus inactivation. Again, more than 4 log reduction of viral infectivity was achieved in the case of potato virus and MS2 virus. Moitza, our colleague, worked on pharmaceuticals removal. She studied for the removal of pharmaceuticals in real municipal wastewater samples, and results yield a higher overall removal efficiency when a combination of peroxide and cavitation was used. And then we come to the challenge. So how can we efficiently exploit the cavitation phenomenon? So we have to build some kind of device, some kind of a reactor, which is, let's say, it consumes a low amount of energy and achieves very intensive or very efficient cavitation conditions. And we think we've done that. So we built a laboratory variation of such reactor, which is great to do some like initial small batch cavitation pit trials. It's cost effective, and the laboratory results can then be used to predict scale-up parameters. We also have a small pilot reactor, which is scalable. It's easy to install. It's plug and play, easy to retrofit in an existing process, and it offers low operational costs. It's robust and fully automated. But now let's jump back in time and see how all of this happened. So I joined the laboratory in 2016, and while laboratory had history with cavitation, as the name suggested, we are a laboratory for water and turbine machinery. The research was also connected to cavitation, but in this sense, it was driven mostly by the questions of cavitation damage and erosion. So investigations were focused in these directions. But at some point, Dular and the guys around him identified that the field could be exploited, in a way of purposeful use of cavitation effects, and they identified a large gap in understanding of the mechanisms behind the degradation, or behind the degradation of organic pollutants. And to solve this mystery got a big European project, so the Year C Consolidator grant, and this was, I think, back in 2018. But at that time, I wasn't working on cavitation. I was working on aerodynamics, and here you can see some images from our, from a project that we worked on. So the Planica wind tunnel. We have collaborated with the architects, or the industry that built this wind tunnel, and my work was mostly condensed about that. After that, I worked mostly on tumble dryers. So we work with a national company that produces white appliances, and my job was to support the company with different development of measurement rigs, measurements, stuff like that. And here in the images, you can see one device which we built for them to test the heat pumps within the tumble dryers. And another interesting device, the guys wanted to evaluate the probability if they could use like the vacuum for clothes drying. So they wanted to build a vacuum dryer. And as stupid as it might sound, we did that, and it was quite fun. Another thing, I'm also heavily investigated in other different like measurement systems, and here you can see a nice project that we did in collaboration with the Faculty of Sports in Ljubljana. So we have equipped a treadmill with measurement cells, so load cells, and did a study on running in different wind conditions. So here you can see the installation of our device in the wind tunnel, and I think we did a nice study on running in windy conditions. Yeah, but if we go from there, I joined the cavitation team somewhere around in 2019. It was a very interesting story. At some point at that time, I was a bit stuck with the fan research I was working on, and my PhD was also stuck, and I was in a strange place. And Brane, the former boss, he saw that, and one time when we were driving from Planica, I think it was one of our last measurements in the wind tunnel, he challenged me to continue the work on the development of the cavitation reactor, so to take over the applicative part of the cavitation research that we did. And I was somehow lacking in the sophisticated scientific work. My work was very applicative, and I said, yeah, sure, yeah, I'll take that. But boy, was I wrong, because even more engineering and I would say unsophisticated work was ahead of me. So here you can see one of our first cavitation reactors that we did. So we started with wastewater treatment and the opportunity or the application of water disinfection. Then we moved to sludge disintegration. It was the time where we moved our pilot cavitation device from a wastewater treatment plant to another wastewater treatment plant, and we cavitated their samples of municipal sludge and did various scientific studies on the effects of the cavitation on the sludge parameters or the sludge properties. And around that time, we first met the guys from the University of Ljubljana, the tech transfer office. They approached us, or I think Mojca found the call to the innovation fund, and we applied for the fund, and we got, I think, around 15K to invest in the technology to build a better pilot, and we did that. And these were, I would say, this was one of the first starts, or one of the first times that we started really thinking about how it would be if we could like somehow commercialize this technology. So the first thing that we had to do is to find like an application or a product. Yes.
Can I, sorry, I cannot raise my hand. I don't find the button.
Yeah,
Can I
no
ask
problem.
a question?
Of course.
Yeah, it's about this sludge disintegration. Could you tell a little bit more of what was the aim of disintegrating the sludge?
This is a good question. So disintegration, that means that you like increase the soluble COD, so the soluble fraction of this sludge. You want to like blow up the cells or the flocks or these cell structures, cell agglomerates. But the goal, I wouldn't say was. It was mostly to enhance the biodegradability. So if you can imagine, you then at some point of the process, you put this sludge into an anaerobic digestion reactor, and you can then like increase the efficiency of that reactor. That is now the idea. Maybe it was even before that, but we didn't approach it at that time. So we are talking 2020. We still didn't really see that. Maybe it will become clearer further on. Okay. So yeah, from there on, we were. This was one of the first applications that we saw. It was the guys from the municipal wastewater treatment plant from Ljubljana. So the picture on the right. They introduced us to the problem of sludge bulking. This is a phenomenon where the filamentous bacteria, this is some kind of like a stringy bacteria, overgrow the sludge in the pool, and instead of sludge like settling down, it floats up to the top of the pool, and it significantly hinders the process of dewatering. So one of the neighboring wastewater treatment plants has had this problem, and we moved our pilot plant to their place to try to help them or to solve their issue, because their current solution was like put a lot of the chemicals in the pool, so destroy all the like bacterial activity, and this was like not, I would say, environmentally friendly, and also very, very costly. So yeah, we introduced our reactor, and we showed that we can mechanically break this bacteria within the sludge if we use the cavitation. And here on the bottom, you can see the samples for different treatment passes. So the treatment amounts of time. So on the left, we have like unprocessed sample where you can see the blanket forming and floating on the top. And then when we move to the right, we can see that we can achieve this sludge settling. So, but wow, there was a catch, of course. So we just didn't have the big enough device. So we could achieve the desired effect in the case of these are so 1 liter samples, but we cavitated I think a few hundred liters first in this I would say the tank of our pilot, and then we moved up to the 1 cubic meter. So you can see this IBC container on the left, and we successfully separated the phases, as you can see on the picture on the right. So we have like a clear phase on the top and like this sediment on the bottom. But when we went to like the real size of the basin, so we have, I think, around 200 cubic meters, we were stuck. So we couldn't make it work. At that time, we also met the guys from the Ljubljana University incubator. So this is like an accelerator, startup accelerator working under the ownership. It's like a separate company, but part of the university. So they invited us to their Labs to Market program. This is a typical, I would say, entrepreneur scientist matchmaking program, where the point of the program is to link, to matchmake, so us, the researchers, and some entrepreneurs. So I would say business-oriented individuals, because as a scientist, you're not looking at like a business potential of the application, and this was lacking. We are lacking in this aspect very much. So as we talked before, we didn't think about business and the revenue and how much money we could make with these applications before. But here at this point, when we joined their program, we started, or they started to ask us those questions. They, of course, it starts very, very gently. So they ask you, I don't know, what is the research you do? How could it be used? How far are you with the this TRL stage, so the technology readiness level and stuff like that? And you feel pretty confident at that point. So you of course, you're a scientist, you know how to explain what you do and stuff like that. Then there comes a problem, because in the audience, we are mostly like non-scientific people. These are business guys in the audience, so these entrepreneurs, and they don't understand what you're talking when you're talking about COD and I don't know, pressure, shock waves, stuff like that. So you need to dumb it down somehow, and of course you need to learn that. And then come the a bit harder question. So like, what exactly is your product? What is the unique value proposition of your product? How big is your market? What is the business model you're pursuing? What is your plan? What's the timeline of your project? What's your financial projection? So we're talking about revenue, profits, cash flow, I don't know what. Do you have the team that can execute this project? And of course, last but not least, do you have the money and the resources to execute this plan? And I would say this was like one of the milestones of our path to commercialization. We engaged in this program. It was, I think, half a year. We were matched with two individuals. So there were one guy was from a company which I think he was like an owner, or he set up wastewater treatment plants. He was director of one and working for a German company that was also developing this wastewater treatment plants and stuff like that and like that. And the other one was from an investment company, like purely money. I wouldn't say this match was very like successful, because we didn't really click. But nevertheless, we've learned a lot through this program. We won the main prize at the end at the demo day they organized, and we also presented the idea to the audience. Of course, you need to learn. There was like a very steep learning curve. You need to learn how to pitch your idea and stuff like that. So yeah, from there on, we somehow switched from these wastewater treatment plant applications, or transition from this kind of applications more into biogas. So biogas production, which is also done could be done in a wastewater treatment plant, or it could be like a separate thing of its own. So you have these agricultural biogas plants that have like no connection to municipal wastewater treatment plants. So the transition was not really hard cut, but like we slowly transitioned to that. And around that time, we also got the ERC proof of concept grant. So Mateusz, or we with the team, like applied for the grant and got the funding. And this funding was mostly meant to find a suitable application. So we went from plant to plant, from wastewater treatment facility to wastewater treatment facility, took their samples, cavitated them in the lab, did the laboratory evaluation of biogas production. So compare the biogas production of non-cavitated and cavitated samples, and then try to build around that. We also had to simultaneously develop the reactor, because when we started, the technology was poor, it was not optimized. We had to overcome a lot of technical challenges. And yeah, around that time, so I think early 2023, we applied for another accelerator program. This was South 3E, which was led by HiSeed Tech from Portugal. This was, I think, also a half-a-year program. It was similar to this Labs to Market program that we engaged in Ljubljana, but it had some benefits. So we were again matched with we got mentoring from two guys from the industry. It's I don't know, you probably all know Veolia. It was a Veolia kind of company, but from Portugal, and they helped us again ask the hard questions. So what is your product? What is your product? What is it that you do? And then based on that, from how to calculate the projection, so to calculate the market size and how this product could be integrated, and what kind of revenue could it generate. We also upped our game in pitching. So here is, I think, one quite good example of when you think about biogas, how to best imagine that. So you all know cows, cattle. So cattle feed on nutrients which they get from grass or from some other organic material. They chew it, and then the anaerobic bacteria living in their gut digest on these nutrients, provide on one side the necessary energy for the cattle to live, and on the other side produce methane-rich biogas and the digestate. So to transition this phenomenon into an industrial process, that's where we use anaerobic digesters. We have a similar structure. So we have some kind of feedstock which we feed into the digester, and in this digester live the anaerobic bacteria which produce the methane-rich biogas, and as a side product the digestate. This biogas can then be turned into electricity, heat, or used as refined to biomethane and used as LPG, so the fuel. And the digestate can be then furtherly furtherly processed to a fertilizer. But what's the catch? We are missing the pre-treatment. So as the cow use chewing to release the nutrients from the organic materials, we want to use cavitation and our cavitation reactor to perform this pre-treatment to enhance or improve the digestion process in the anaerobic digester. And after, I would say, I don't know, somewhere near the end of this program, we found our potential application, or one of our, like, I would say, one of the companies which could implement our technology, and they have their own, like, this anaerobic digestion process. It's a bit specific. It's not like in the picture. So you take this organic waste and put it through our cavitator, but they have like a two-stage anaerobic digestion, and when we can come into the process in this second stage, and that's where we can achieve very high improvement of the biomethane potential. So we can gain approximately 30%. We can improve the biomethane yield by 30%. And on the other side, we found another pain point. So this digestate then needs to be also like post-processed or released into a wastewater treatment plant, and they have like their own in-house wastewater treatment plant. And if we implement or integrate the cavitation in their process, we can reduce the COD, so the chemical burden of this outlet, effluent, however you call it, also by approximately 25%. And this is also a major benefit for them. And yeah, right now we are in the process of the installation. The company that we pitched the idea to has agreed to buy our product, so our cavitation reactor, and I think we will do the installation sometime next week, maybe already on Monday. I don't know. So yeah, this is like. I would say this was our journey till now. I would picture it as very like wavy, turbulent, and overall hard, because you need to learn a lot on the go. You don't know anything about. I mean, at least I didn't know a lot about the commercialization or the company formation or the, I don't know, product sales and stuff like that, as I was like more technically oriented. We had to learn that on the go, and the process, this sales cycle. So from the, I don't know, first time where we met this potential client that has now become our client, as they have bought our device, and to this point of installation and point of where they actually ordered our product, like this was like more than a year. And I don't know, it seems really like long, and it's hard to close. And also, you know, in this path, I had like some, I mean, every like researcher or everyone in this environment has like some personal stuff, and I was also navigating the PhD studies, and yeah, it can be really tough on the times. But nevertheless, maybe a few words on the spin-out ecosystem at the University of Ljubljana. The University of Ljubljana has some experience with spin-outs. I think there are around 20. There has been around 20 spin-outs in the last 10 years. So approximately 2 spin-outs per year. But I think the common notion of also the university and the faculty is that spin-outs are not yet like a common practice at the university. Especially, I would say, for our faculty hasn't had a spin-out. So this aspect is also a bit challenging for us to manage. Because maybe to point out, here in Ljubljana, we also have some institutes, and I would say Jožef Stefan Institute is one of the places which generates much more spin-outs. They have, I think, about more than 40 spin-outs, and some of them are like super successful. So in the recent years, I would say momentum and the interest to grow spin-outs from the university has really risen, and the engagement of the university is therefore, I think they're very interested to build a spin-out with us. So they help us in many ways. They organize different like events and workshops to promote to the transfer of the technology, and we also engaged in some of such like calls. So we went for the Rector's Award in 2022 and won second place. And this is one of the things that I think is also like like a good thing for a spin-out in the making to engage in. So to find the environment or the help that the environment can offer. So in the University of Ljubljana, we have a technology transfer office that organizes these innovation funds. We have applied for 2 innovation funds so far, or we have got the funding from the 2 funds, totaling, I think, around 75,000 euros. And we have participated in this Rectors Award. Besides that, they organized the Uniminds Festival, connecting industry or somehow linking the industry interests with the university's know-how or the university's environment. They have a weekly newsletter on the industry challenges. They do some promotion of technologies, and they help us a lot with the IP management. And yeah, on the other side, as I mentioned, we have LUI, so University of Ljubljana Incubator, which was established as a part of University of Ljubljana to foster like entrepreneurship and innovation. They offer different mentorship programs, workshops and trainings. And as I mentioned, we were engaged in the Labs to Market program. And they also offer a lot of networking opportunities, because, you know, if for us right now, we are looking for different applications and different places where our technology could be integrated, and they can offer us a lot in this manner. They can link us to different companies, different spin-outs who also work with I don't know, in food processing, in farm and stuff like that. And this is very important when building a product. Our experience with them is, as I mentioned, this Labs to Market program, and we regularly engage in their workshops, and we also have like a dedicated mentor there. So one thing I would like to point out for the end is that it's very important for both, for the university or the ecosystem, or the like basic company where the spin-out is coming from, to recognize the benefits of a spin-out, and on the other side, for the company that wants to like fracture, to recognize the benefits that we get as a spin-out. So on one side, the university gets to showcase the impact, to get the knowledge exchange pipeline, to increase their like research resource potential, and at the end to attract talent. So to showcase that you don't have to go to work for a corporation. You can like build like your own company within, or like from the university environment. And on the other side, for the spin-out, is very like the benefits of a spin-out is the access to the IP, the access to the expertise, to the equipment, to the know-how of the university environment. We instantly get credibility and reputation, because if you brand yourself like a spin-out company, it's normal that you don't have any track record, you don't have revenue, stuff like that. And of course, you get to the talent pipeline. So you can instantly find like some students or some potential employees for the company, which is also very important, because the point of the company is to like replicate and to grow stuff. So also to grow this human potential. So yeah, lessons learned. Building a spin-out is hard, but it can be rewarding. It's a great, of course, a steep learning experience, and it can also be fun. And a few like suggestions or like thoughts. If you have an idea, if you want to spin out, if you want to build a product, talk to your clients. Your clients should love the product, because it solves their pain 10 times better than they currently do. And find the support among your peers, from the laboratory environment, university environment, faculty environment, I don't know, like local startup ecosystem environment, because you will need it. That's all from my side. And if you're looking for a new challenge, join us at CAVI. Thanks.
Thanks a lot, Jurij, for this insightful lecture.